This is a video to work out the problems on the Chapter 5 test review sheet. And so let's just get started working these problems out. Given these two functions, the f and the g function, this says to add those functions together. And what would that result be? So let's see. We have 3x plus 2. That is the f function. And then we're going to add to that x squared minus 2x plus 1. This is the g function. Now we just combine like terms. There's only one quadratic term, x squared. We have 3x minus 2x, that's positive 1x. And then we have these constants, 2 plus 1 is 3. So f plus g of x would equal this, x squared plus x plus 3. Number 2 is taking those same two functions and subtracting them. So we'll start with the f function, the order that it's given in the problem, 3x plus 2, and then we're going to subtract the g function, x squared minus 2x plus 1. I'm going to remove the parentheses, distributing negative 1 to this group. So 3x plus 2 minus x squared plus 2x minus 1. And then once again we'll combine like terms and we end up with negative x squared, and then 3 plus 2 is 5x, and then 2 minus 1 is plus 1. So f minus g of x is equal to this trinomial. Okay, so be careful with subtraction. A lot of people miss subtraction, and if you put this second function in parentheses and distribute negative 1, I think it's a good idea. Helps you to avoid those common mistakes that usually arise with the subtraction problems. Okay, so same functions, but this time we're going to multiply them together. So this is a binomial, the f function, times a trinomial, the g function. And so we'll take this f function and we're going to distribute both 3x and 2. Okay, so let's start with distributing 3x to each one of these. 3x times x squared is 3x cubed. 3x times negative 2x is negative 6x squared. And 3x times 1 is 3x. And now I'm going to keep going, distributing 2 to each of these terms. 2 times x squared, 2 times negative 2x, and 2 times 1. And now we'll combine like terms, and we'll just put our answer up here. There's only one cubic term, x to the third. That's 3x to the third. And then the quadratic terms, negative 6 plus 2 is negative 4x squared. The linear terms, 3 minus 4 is negative 1x. And then finally this constant, plus 2. So there's the answer for f times g of x. And then finally we have division. The f function divided by the g function. Okay, so that's your answer to the division, but you got to be careful when you're dividing. If there's a variable in the denominator, then we're going to have to place restrictions on the domain. Remember, we cannot allow division by 0. And there is a certain number that if we did allow it to be an input, that's exactly what would happen. So how do we know what that number is? Well, you can always take this denominator and solve it. It's a quadratic. Make it equal 0, and you'll find out exactly what numbers would plug in for x to cause this denominator to become 0. And the easiest way for me to solve a quadratic equation is by factoring if it's possible. And factoring is possible here. It's the quadratic, or the binomial x minus 1 multiplied by itself. So when x is 1, if we let x be 1 as an input in the denominator, it would become 0. So we need to place a restriction on our domain. We need to limit what the domain can be. Domain means allowable numbers to be put in for x. Well, any number could be put in for x except for 1. We cannot let x be 1. If we do, then we would get 0 as a denominator. So that's our complete answer for f divided by g of x. Okay, moving on to the next set of problems. Number 5 says, let's multiply 3 times the f function. 3 times both of these terms will be negative 3x plus 3. And then we're going to subtract the g function from that product. Okay, so let's take care of this in the left parenthesis first, these function operations. And let's go ahead and combine like terms. Negative 3x plus 3 minus 4x minus 2. And that gets us to negative 7x plus 1. Okay, now this 2 does not mean multiplication. It means an input. Okay, just like later on we're going to see expressions like this. Input 2 into the f function, and then whatever that gives you, you'll input it into the g function. Well, the 2 in this case is acting the same way. It means input 2 into the result of 3f minus g. Alright, so I'm going to let x become 2 and simplify. Negative 14 plus 1. So my answer for number 5 is negative 13. Okay, very much the same way here for number 6. I'm going to multiply 2 times all of the members, the terms of the f function. That gives me negative 2x plus 2. I'm going to divide that result by the g function, 4x plus 2. And then I don't really have any way to simplify this. Now I can just go ahead and input 3 for both of these x's. Now that I've done this operation, now I'm going to input 3. Okay, so negative 2 times 3 plus 2 divided by 4 times 3 plus 2. Negative 6 plus 2 is negative 4, and 12 plus 2 is 14. And then when you reduce or simplify, you get negative 2/7. And that's the answer for number 6. Okay, similar problem here with number 7. Let's start with the h function. And we're going to subtract from that the product of 4 and the f function. Okay, so I just brought subtraction down, and now I'm going to do 4 times f. Negative 4x plus 4. Okay, and let's simplify this. X squared minus 1 plus 4x minus 4. X squared plus 4x minus 5. That's the simplified form of h minus 4 times f. Now we're ready to use negative 2 as an input. Both of these x's will become negative 2. Alright, so negative 2 squared is 4, minus 8 minus 5. Simplify this. 4 minus 8 is negative 4. Minus 5 makes negative 9. So that is your answer for number 7. Alright, the next type of problem, these are called composite functions. Remember we did these, practiced these a few days ago, several days ago, and the way it's written, you always begin using 2 as an input into the closest function written to it. So the first thing I'm going to do is g of 2. So you can kind of think working inside out. Let's find out what g of 2 is. That means use 2 as an input in the g function. Alright, so you always square first. 2 squared is 4, and 4 times negative 3 is negative 12. Now negative 12 becomes an input into the f function. So let's find out what f of negative 12 is. 2 times negative 12 plus 3. Negative 24 plus 3 makes negative 21. That's your answer for number 8. Okay, number 9 says use negative 5 as an input in the f function first. So let's determine f of negative 5. Okay, negative 10 plus 3 is negative 7. Now negative 7 becomes an input into the g function. So let's figure out what g of negative 7 is. Negative 3 times negative 7 squared. Powers first, so that's negative 3 times 49. And if you do negative 3 times 49 is negative 147. So that's your answer for number 9. And then finally, number 10. We start off by, again, closest function to the number first. So let's do f of 6. F of 6 is 2 times 6 plus 3. 12 plus 3 is 15. And now we're going to do h of 15. Well, for the h function, it always results in a constant. Okay, no matter what you do as an input, you're always going to get 2 as an output. It's called a constant function. So even though we're inputting 15 here, the result is still 2. And that's always going to be true for this particular function, no matter what the input is. So my answer for number 10 is 2. Okay, moving right along. Now we get into some graphs. Find the inverse of each function. I'll just go ahead and do that first sentence first. To find the inverse of a function, we switch places with x and y. So I won't do this every time, but remember, whenever you see f of x, you can pretend as though it says y. You're not changing anything if you do that. So now you can see that x and y need to be switched. So that's always step 1 when you're finding the inverse of a function. Switch places with x and y, and now solve for y. And that would mean, first of all, adding 6 to both sides, and then dividing by 5 on both sides, or you could think multiplying by 1/5. And since this is the inverse, I'm going to use inverse notation. So that represents, if that's f, if I started with f, this represents the inverse of f. And here's another way. If you go ahead and divide both of these by 5, you could write it as this. Either is acceptable. So that is my answer. Either one of these would be okay for finding the inverse of the function. Now let's graph both the function, which is given, and the inverse on the same coordinate plane. So this is a line. X to the first means it's going to be linear. So here's my y-intercept, negative 6, and slope of 5. Up 5, right 1. And you would get your ruler, straight edge, and we'll draw a straight line through those points. Okay, so that's pretty close. There's my graph of the function, and now let's graph the inverse. Well, you don't have to graph from this inverse function. It's okay if you do, but it's a lot easier just to take points off of the function. You can see 3 points that we drew our line through. Just take those 3 points and switch places with the xy coordinates. Let me show you. So down here in red, this is the point 0, negative 6. If I wanted to plot a point on the inverse, I could take that point, switch places with the xy coordinates, and plot negative 6, 0. It's as easy as that. Same thing here. I'll take the point 1, negative 1. I'll write that out in red so you can see it. For the inverse, I'll just switch those, and I'll do negative 1, 1. Okay, one more time. Let's take this point, which is 2, 4. And when I turn those around, switch places with them, I plot the point 4, 2 for the inverse. And that's always a way that you can get the inverse graph. Right? And so the blue represents the inverse. The red represents the what I'd call the original function. That's your complete answer for number 11. So let's try number 12. Number 12 is a quadratic equation. It's in standard form, it's in vertex form, sorry. It's in vertex form, which makes it nice, and it's actually a translation of the parent. The parent f of x equals x squared. Remember that? That looks like this. You can start with this parent, and you can shift those points on the parent 2 places to the left and 3 places up. Okay, so as I move them, I'll just delete. So starting here, I'm going to go 2 places to the left and 3 places up. Takes care of that one. 2 left, 3 up. Takes care of that one. 2 left, 3 up. That one's done. And 2 left, 3 up. And that's the function. That's the function that's given. All the points on the parent were translated. Again, the word translate just means transfer. And so there's the graph of the parent, f of x. And so let's go ahead and get the graph of the inverse real quick, just like we did before. Let's take ordered pairs from the original. So this is negative 2, 3. To get the inverse, I'm going to do 3, negative 2. This point on the red is negative 1, 4. So let's plot 4, negative 1. This is negative 3, 4. So we'll do 4, negative 3. This point in red is 0, 7. So for the inverse, we'll do 7, 0. And this is negative 4, 7. So we'll do 7, negative 4. And those blue dots will represent the graph of the inverse. Okay, we still haven't found the inverse function, so once again, we'll switch places with x and y. And solve for y. So the first step in doing that will be subtracting 3. Now we'll do the square root of both sides. Don't forget plus minus. And then you can subtract 2. And this is the inverse function. All right. Very good. All right, one more. This is not a translation of the parent function. This is a quadratic. It is going to result in a parabola. So probably the easiest thing to do is just to do a little table of inputs and outputs, domain, range. I showed you on the review sheet just the answer key. A quick way to find the vertex if you don't want to try to find it through the table. I think finding the vertex is quicker. You can always use this little formula, and I think this is a better way. This works with absolute value functions and quadratics where we don't have where we have something other than the parent. Notice the parent always has just a 1 coefficient here. So other than 1 as the coefficient, we can't just treat this as shifting the parent, for example, 1 to the left. It's not quite that simple. But we can use this little formula, and let me just label the parts. M is in front of X, B is this other number in the parentheses, and then C would be out here, either added or subtracted. So when we put all that together, we get a vertex of -1/2 for the X and 0 for the Y. There is no number outside, so that's a good place to start. And now it makes it easy to know what to use as inputs. Just pick some numbers around -1/2, like 0. Okay, if X is 0, you get 0 plus 1, which is 1 squared, and that's 1. And our reflection line, our line of symmetry, is X equals a -1/2, so that means on the other side of that line I can make another point. Okay, now let's just choose one more input, like X is 1, so let's evaluate f of 1. 2 times 1 is 2, plus 1 is 3, and 3 squared is 9. So 1, 9 is up here. That's 1.5 spaces away from the line of symmetry to the right. So I can do another 1.5 to the left and match it up. And I can use those dots, connect them. And that represents the graph of this function, f of x. So now let's graph the inverse. So take these ordered pairs, starting with the vertex. The vertex is at -1/2, 0. So for the inverse, I'm going to do 0, -1/2. Okay, this is the point 0, 1 on the red function. So let's plot 1, 0 for the inverse. This is -1, 1 on the red, so 1, -1 on the inverse. We figured this to be 1, 9 on the red, so 9, 1 will be on the inverse. And this is -2, 9, so we'll do 9, -2. And that blue parabola that opens to the right is the inverse graph. And now let's find the inverse function and we'll be done. So remember, switch places with x and y and solve for y. So the first thing we'll need to do is the square root of both sides. Then you can subtract 1. And then finally divide by 2. And this is the inverse function. And that's it for number 13. Okay, 14 and 15, same type of problems. We want to know if these are inverse functions. If they are, then when I do this composite, f of g of x, I will get x, and I will also get that same result if I turn this around and do the composite g of f of x. So if these are the results, then I know that these are inverses. So we got to test them. So let's do f of g of x. That means to take the g function and put it into the f function in place of x. Use it as an input. So here is f of g of x. All right, so g into the f, 2 times, now I'm going to put the g function, 1/2 x minus 8, and then plus 16, and distribute the 2. This is x minus 16 plus 16, and simplified we get x. All right, that checks out. And now let's go the other way because we still don't know for sure if they are inverses. So let's do the g of f of x composite. This time the f function will be an input into the g. 1/2 times 2x plus 16 minus 8. Distributing 1/2, we get x plus 8, bring down minus 8, and we get x. So we got x when we did both composites. So these are inverses. My answer for number 14 is yes. Okay, same thing on number 15. We'll start with f of g of x, inputting g, the g function, into the f. -6 times 8 minus x over 6 plus 8. When you multiply by -6, these would cancel, leaving -1 times 8 minus x plus 8. And when I distribute -1, I get -8 plus x plus 8, and that equals x. So that checks out. So let's see if the g of f of x checks out. This time f into the g. 8 minus, and now we're going to replace x with -6x plus 8 divided by 6. And I'm running out of room here. Let me see if I can squeeze this in. 8 plus 6x minus 8 over 6. So let's do some mental math. 8 plus -8 is 0. So these are just going to become 0. You're left with 6x divided by 6. 6's would cancel, and you are left with x. So that checks out. So these are also inverses. So just do your check. F of g of x, g of f of x, you must get x in both cases for these to be inverses. If you get x with one but not the other, they're not inverses. Okay. All right, let's graph some square root functions. Once again, this is not a translation of the parent, so we're just going to do some inputs and outputs. But we got to remember that for inputs, appropriate domain numbers, we've got to avoid this becoming a negative number when we input for x. So for example, I couldn't use -1 as an input because that would give me the square root of -3, which is not a real number. So I got to keep in mind that yes, I can input anything I want, as long as those numbers fit this description. In this case, they have to be greater than or equal to 0. So let's just do some inputs. If I do x is 0, then f of 0 is 0. Let me just do f of 2. So this would be the square root of 6. So you might want to grab your calculator, and the square root of 6 in decimal form is 2.45. I'll just say 2.4. And then maybe a non-decimal, like if I let x be 3, we get the square root of 9, which is 3. Okay, and that should be good enough. Here's 0, 0. Here is 2, and then just about 2.5. 2.4, and then 3, 3. And we can use those. It'll go through those and then keep on going upward as we choose larger numbers. So it's got a curve to it. It's going to keep on getting bigger as the numbers for x get bigger. And let's see. We're supposed to state the domain and range for these. So the domain, we've already stated. Domain has to be all numbers greater than or equal to 0. For the range, same thing. We're going to start at 0, and our numbers for y are just going to continue to increase as we go to the right, choose larger numbers for x. So we'll state the range as this. And that's it. That is your answer for number 16. Okay, number 17 is it's a transformation of the parent function. Hopefully you can see it. F of x equals the square root of x. So I'm going to start with those points that we use to identify the parent. You can use these same points every time. Instead of doing inputs and outputs, I think it's easier just to take these 4 points representing this parent function, and we're just going to count out really 3 things that will be taking place on these 4 blue dots. Okay, so first of all, let's start with this 2. Multiplying by 2 means you're multiplying the y coordinate of these dots by 2. Okay, so the y coordinate of the origin, of course, is 0. And 2 times 0 is 0. So multiplying this point by 2 has no effect. When I look into the radical, I see that this is telling me to move left 2 and then down 3. And so that point that started at the origin for the parent is now down here, left 2, down 3. All right, here I am at 1, 1, y coordinate 1. When I multiply by 2, it makes it 1, 2. Okay, now do left 2 and down 3, and we can erase this point now. It's been transformed. Okay, let's move over to 4, 2. When we multiply by 2, it makes it 4, 4. Then left 2, down 3. Takes care of that one. Here we are at 9, 3. 9, 3. But when multiplied by 2, it makes it 9, 6. And then we can do left 2, down 3. And so my 4 red dots represent the graph of the answer. And then it's just a matter of doing the domain and range. Domain will be all x such that x is greater than or equal to negative 2. You can see that from negative 2 to the right. And the range will be f of x such that, okay, it starts here and it's going upward. So it starts at negative 3 and gets bigger. So f of x is greater than or equal to negative 3. And that is your answer for number 17. Okay, same approach on number 18 because this is the parent function. So I'm going to start off the same way. These dots in these places. Okay, so now this time we're multiplying by a negative. Remember, multiplying by negative has the effect of flipping this parent over the x-axis, and we'll be able to see that as we work our way through this problem. So again, start with your origin point and multiply the y coordinate only by negative 3. Well, that doesn't change the origin because 0 times negative 3 is still 0. Now this indicates a move right 1, and this means up 2. So here I am with my origin point. I'm going to go right 1 and then up 2, and there's the origin after it's transformed. Okay, here I am at 1, 1, but when I multiply by negative 3, it makes it become 1, negative 3. Then I do right 1, up 2. Okay, 4, 2, when multiplied by negative 3, becomes 4, negative 6. Right 1, up 2. And then 9, 3, when multiplied by negative 3, becomes 9, negative 9. Right 1, up 2. And that will take care of this graph. Okay, now let's do domain and range and we'll be done. Domain will be all x such that x is greater than or equal to 1. The range will be f of x such that, okay, so we're starting at 2 and we're going to go down forever. F of x is less than or equal to 2. There's your answer for number 18. Now we get into cube root functions. And remember, this isn't the parent cube root function. The parent would not have a 2 in front of it. So translating the parent, it would have to look like this. So much like we did with our problem number 16, we're going to do a little table of values and just come up with a few inputs. Now remember the domain here for the cube function, the cube root function, the domain is all real numbers because it's okay to have the cube root of a negative number. That's certainly able to be calculated. It's just for the square root function we cannot let this radicand become negative. So I'm just going to do some inputs. F of 0 would be 0. Alright, it really doesn't matter what you choose. You can do f of 2. You'll just, in this case, you'll need to grab your calculator and figure out what the cube root of 4 is. And I've got my calculator here. Looks like 1.587. We'll say 1.59. A little bit more than 1.5. 2. We'll just put it right there at 1.5. And then if you wanted to use some perfect cube numbers, or that would create a perfect cube number, you could let x be 4 because the cube root of 8 is 2. And then be careful because the domain for this cube root function is all real numbers. And if you were to graph just this, you're not showing all real numbers. You're only showing numbers that are greater than or equal to 0. So if you choose a positive number as an input, make sure you choose the negative. So for -4, -2. So this would be the cube root function graph. And the directions don't tell us anything about doing domain and range on this one, so that would be your answer. Okay, now number 20 is a translation of the parent. So I'm going to draw points that represent the parent. 8, 2, the cube root of 8 is 2, and -8, -2. So I'm just going to use those as a reference because what this function is telling me is to take each of those points and go left 4 and up 1. Alright, so if I go left 4, I'm just going to approximate, and up 1, I'll say that's there. 1, 2, 3, 4, up 1. 1, 2, 3, 4, up 1. 1, 2, 3, 4, up 1. And 1, 2, 3, 4, up 1. And the blue dots, just draw a curve through those. And that represents a translation of the parent function y equals the cube root of x. And you're done. Okay, one more. This time it's going to be a transformation because multiplying by -2 is going to take our parent points and reflect them over the x-axis. Okay, so we'll start with those parent points. And just like we did before, we're going to multiply the y coordinates only by -2. So -8, -2 When we multiply by negative 2, it makes negative 8, 4. And then we can go right 1, up 2. I'll do this one in blue. Alright, so negative 8, 4, right 1, up 2 is there. Okay, y-coordinate here is negative 1, but when we multiply negative 1 times negative 2, we get positive 2. And then we can go right 1, up 2. That one's done. Multiplying by the origin doesn't change it. So we can just do the right 1, up 2. Alright, this is y-coordinate 1, but when we multiply by negative 2, it makes negative 2. Right 1, up 2. And this is y-coordinate 2, but multiply by negative 2, it makes negative 4, right 1, up 2. And we've got the blue dots that we'll use to draw our graph. I missed that bottom one, but I guess that's close enough. So you can see how multiplying by a negative makes a flip over the x-axis. Okay, so we're getting into solving equations. So remember, the idea behind solving these radical equations is to isolate the radical first. I need to subtract 4 from both sides in this equation first. And now I'm ready to undo the square root of by squaring on both sides. 3x minus 1 is equal to 16. Add 1 to both sides. 3x is equal to 17. X is equal to 17 thirds. It's always a good idea to check these. I'm going to go through just a mental check. 3 times 17 thirds is 17. The 3's would cancel. And 17 minus 1 is 16. The square root of 16 is 4. 4 plus 4 is 8. So that is a good solution. Number 23, same idea is true. We need to isolate the radical. And the radical, even though it doesn't look like it, the radical of this problem is this part in parentheses raised to the 1/3. I'll keep trying to remind you of this because this could just as easily been written as the cube root of 3x minus 1. So it's still true. I need to isolate the radical first. So my first step in doing that will be to add 6. My next step would be to divide by 3. Now I can undo raising something to the 1/3 by raising that to the 3rd. And I have to do that, of course, on both sides. So I'm going to get 3x minus 1 equals 8, 2 to the 3rd. Add 1 to both sides. And I get x is 3. Let's check it. 3 times 3 is 9. 9 minus 1 is 8. The cube root of 8 is 2. 2 times 3 is 6. And 6 minus 6 is 0. So that checks. Okay, now we're solving radical inequalities. My first step here is to take the radicand and make it greater than or equal to 0. Remember, this radicand has to be a number that is positive or 0. And so we're going to find out what values for x will make that happen. In other words, we're going to find out what the domain of this inequality would be. So I add 1 to both sides, I solve for x, and I get x is greater than or equal to 1/3. My solutions have to fit this description. So now let's go through the process of solving, much like we did with the radical equations. So my first move would be to subtract 2 from both sides. Now I'm going to raise both sides to the 2nd power. That gets rid of the radical, and I get 3x minus 1 is less than 9. Add 1 to both sides. 3x is less than 10. X is less than 10 thirds. Okay, Well, I do have a number. 10/3 is greater than 1/3. And my solution says I can use any number less than 10/3. Well, that's not exactly true, because if we go too low, we're going to violate what we said the domain has to be. To keep this from being the square root of a negative number, x has to be a number bigger than 1/3. So what we're looking at here is really a situation of numbers between. They can be less than 10/3 as long as they don't go below 1/3. So we're going to state our solution as all the numbers between these. And I used or equal to here because that's the way the inequality is stated. And so that would be my answer for number 24. X can be less than 10/3, but it has to be greater than or equal to 1/3. Or in other words, x has to be between these two numbers. Number 25, whenever you have radicals, two radicals, you need to make sure that they are on separate sides of either the equation or the inequality. Since this is an inequality, we're going to figure out what the domain has to be in both of these cases to prevent the square root of a negative number. Okay, so x has to be greater than or equal to negative 1/3 for this, and greater than or equal to negative 6 for this radical. Okay, so now let's separate these radicals. Let's put them on opposite sides. I can just add the square root of 6 plus x to both sides. Now do the square, or not square root, but raise both sides to the second power, square both sides. That gives me 3x plus 1 is greater than 6 plus x. Get the x's together. I'm going to subtract x from both sides. I'm going to subtract 1 from both sides. And I get x is greater than 5/2, or 2.5. So I'm going to see, do my numbers that are represented in the solution agree with what they have to be to avoid the square root of a negative number? All the numbers bigger than 5/2 certainly agrees with all the numbers bigger than or equal to negative 1/3 or negative 6. So this ends up being my solution to number 25. Okay, number 26 is a chapter 1 review problem. So let's take a look at graphing each one of these. We need to solve them for y. We'll take this top one and solve it for y, get it in what we would call slope-intercept form so we can graph the boundary line. So I'm going to subtract x from both sides. Alright, let's go ahead and graph this boundary line. It has a y-intercept of 1.5 and a slope of negative 1/2. And since it says or equal to, that's going to be a solid boundary line. Okay, now let's do this one in blue. Solve for y. 3y less than or equal to 2x plus 1, dividing by 3. This one has a y-intercept of 1/3 and a slope of 2/3. Up to right 3, up to right 3, and we can sketch this boundary line. Also solid. Oh, change the color. All right, and now let's do the shading. And this says for the red line, we're going to shade the greater than side, which is above. Okay, I'm just pointing to the above side. For the blue line, it says to shade the less than side, which is below. And the solution to these linear inequality problems will be the graph, and it's where the two shadings combine. So the answer is going to be this shaded area where the red and the blue shadings would meet. Greater than means above the line, less than means below. And there's your answer for number 26. Okay, so for number 27, whenever you have this complex number in the denominator and you're asked to simplify, you use what is known as the conjugate. And the conjugate of 2 plus 4i is 2 minus 4i. You just change this sign in the middle. And now we're just going to multiply on the top. I'll just bring this down here. Distribute 5 to both of these. 5 times 2 is 10. Minus 5 times 4i is 20i. On the bottom, we could use FOIL. 2 times 2 is 4. And then this would be minus 8i plus 8i, outer and the inner. And then this would be minus 16i squared. But I want to simplify this. You notice that the 8i's cancel each other. Okay, so let me just come down here and we'll bring it down to this. 4 and then minus 16i squared. Well, anytime, to make sure you remember this, anytime you are left with I squared and you're asked to simplify, you need to replace I squared with negative 1. Okay, I squared is literally equal to the number negative 1. So if I replace I squared with negative 1, now it becomes 4 minus negative 16, which is another way of saying 4 plus 16, which is 20. Okay, so hopefully you saw that. And now it's just a matter of writing this as a complex number. I'm going to go ahead and divide by 20 in both cases. Oh, that should be 20i on the top instead of 2i. Okay, so 10 over 20, that's 1 over 2. Minus 20 over 20 is 1i. And that's it. That is a complex number form. The real number goes first. I always goes last in complex number form. It looks like this, a plus bi. All right, 28, we'll multiply the numbers, the real parts. Negative 5 times 3 times 4, that's negative 60. And then I times I times I is I to the third. And I to the third, let's go back and talk about something we mentioned a few weeks ago. I to the first is just I squared, we've already mentioned, is negative 1. Well, I to the third is just these two multiplied together. So negative 1 times I is negative I. So you could rewrite this as negative 60 times negative I. Negative times negative is positive, makes 60i. And that's your answer for number 28. Okay, 29, solve algebraically. First of all, let's treat this as an equation, a quadratic equation that needs to be solved. It can't be factored, so you could use either the quadratic formula or completing the square. I'll just use quadratic formula. So the opposite of b plus minus the square root of b squared minus 4 times 2 times negative 9, that's subtracting negative 72 all over 4. Okay, so this is going to be the square root of 88 over 4. All right, so we need to find out what the square root of 88 is as a decimal. And that is 9.38. Okay, so using our calculator, let's find out what negative 4 plus 9.38 is, and then we'll divide that by 4. And then we're going to do the same thing with negative 4 minus 9.38 divided by 4. Now be careful, if you're going to do all of this in your calculator at once, you'll need to put parentheses around the numerator. Okay, so let's see if we get the same thing. Negative 4 plus 9.38 divided by 4 is 1.35 rounded. And we'll do the same thing with negative 4 minus 9.38, and that's negative 3.35. Okay, so these numbers represent, we're going to take a number line, and we're going to break our number line up into 3 parts based on these numbers. All right, and then what we're going to do to solve this inequality is we're going to choose numbers in each of these areas and then plug them into our original and see if it makes this statement true. So a number to the left of negative 3.35, we could say negative 4. A number in between, we could say 0. And then a number to the right, we could say 2. All right, we'll take each of those and we'll plug those numbers in one at a time, and then we will see if we get a true statement. Okay, so we have our numbers that we're going to use to test, and I've written them here in red. So one at a time, let's take these numbers, plug them in for x, and see if it makes the inequality true. So we'll start with negative 4. If we substitute negative 4 in for x, it would look like this. And do we get a true statement out of this? So this would be negative 4 squared, which is 16, times 2 is 32. And this would be minus 16. So 32 minus 16 is 16. That is greater than 9. So what we can conclude is all the numbers that are less than negative 3.35 would be part of the solution. They would make this a true statement. Okay, so now we're going to test the interval between these two numbers. And I just picked 0 because that's an easy one to test. So if I let x be 0, I get 0 is greater than or equal to 9. Well, obviously that's not true. So the numbers in between negative 3.35 and positive 1.35 are not part of the solution. And so now let's test this number to the right, positive 2. So 2 times 2 squared plus 4 times 2. And let's see, is that greater than or equal to 9? So 2 squared is 4, times 2 is 8, plus 8 is 16. That is definitely greater than 9, so these numbers do work. So now we're ready to express our solution. And it's going to be those numbers that are less than or equal to negative 3.35. That's part of the solution, and we'll combine that with all of these numbers that are greater than or equal to 1.35. And that is your answer for number 29. And we have one more, number 30. We have this equation. It's a quartic trinomial, and we're going to see if we can solve this by factoring. So if it's able to be factored, to know whether or not this can be factored, you can multiply these terms on the end. 8x to the 4th times negative 3, that's negative 24x to the 4th, and then just see if there are factors of negative 24x to the 4th that would add up to 10x squared. And there are a pair of factors that would make that possible. If we did 12x squared times negative 2x squared, they would definitely multiply to give us this, and then if you added those two together, you would get this middle term. So I know factoring is possible, and this is a good time if you want to. I'm going to leave that up to you, but it's a good time to pull out the old box method. And we've already found out these terms that would go in these other boxes, and it doesn't matter in which order you place them. Find the GCFs of each row and each column, and you'll have your factoring. So 4x squared would be the GCF of this top row of numbers. Down here would be minus 1. This way would be 2x squared, and this way would be 3. So that shows us the factoring. 2x squared plus 3 times 4x squared minus 1. And when you get it factored, the way you solve these is to let each factor equal 0 separately. Just treat each factor as though it were an equation equal to 0 by itself. And then go about your normal routine to solve for x with each of these equations. So I'm going to subtract 3 from both sides here, divide by 2, and then I'm going to do the square root of both sides. Don't forget plus minus. And since I'm doing the square root of a negative number, I'm going to need the number I to represent my answer. And for now, until we cover rationalizing denominators, I'm going to say that this would be an acceptable answer. But just to kind of give you a preview of where we're going, it is not mathematically acceptable to leave a radical in the denominator of a fraction like this. So the way we take care of that, this is called rationalizing. We would multiply, if it's a square root, we just multiply by the square root on the top and bottom, and that would give us the square root of 6 over 2 plus minus. That's really a better answer, but until we get there in this class, I'm going to say that this is also an acceptable answer. So remember, the degree of the polynomial will tell you how many solutions you are supposed to solve for. We found 2 of those solutions, and now let's find the other 2. So 4x squared is equal to 1, x squared is equal to 1/4, and then when you do the square root of both sides, this is going to be plus minus a half. The square root of 1/4 is 1/2. So that represents the other 2 solutions. Alright, and so the whole idea here is to set up the factoring, and it's the factoring that should be able to pretty easily lead you to the 4 solutions. And that is your review sheet for Chapter 5. Hope this helps you out. If you have any questions, let me know.